Over 4 days in December, 4 rockets lifted off from 4 different spaceports across China. Hainan, Taiwan, Jiuquan, and Xishan all executed successful orbital missions within a 96-hour window. Launching a payload into orbit is notoriously difficult, but coordinating 4 independent launch campaigns in under a week requires a vast, highly synchronized industrial machine operating at peak efficiency. At the core of this machine is the Weixing, or artificial satellite. For decades, building one of these spacecraft meant handcrafting a bespoke piece of hardware. Today, Chinese aerospace engineers have largely abandoned that one-off artisanal approach. Instead, they rely on a structural foundation called a satellite bus. A bus is a standardized chassis that provides the essential power, thermal control, and propulsion systems, onto which engineers can bolt whatever specific sensors or communication payloads a mission requires. Historically, a single custom satellite took 3 to 5 years to design and build. To deploy massive broadband and observation networks in low Earth orbit, you need thousands of active units ready to fly. To meet that kind of volume, China had to tear down its old manufacturing methods and build a completely new production pipeline. You can see the result of that shift at places like the Shanghai Microsatellite Engineering Center. This facility operates as a 智能工厂, or smart factory. Rather than engineers hand-soldering every connection, the facility uses artificial intelligence to manage inventory and robotic arms to execute precise, repeatable assembly tasks along a modular production line. By standardizing the parts and automating the labor, these automated production lines can cut development cycles by up to 80%, allowing a single facility to churn out as many as 300 satellites a year. Behind these massive production numbers are giant state-owned enterprises like the China Aerospace Science and Technology Corporation, or CASC. They act as anchor tenants for regional industrial hubs, supplying the steady capital and deep talent pools required to keep the assembly lines moving. But volume alone doesn't guarantee success in orbit. Before any mass-produced unit is strapped to a rocket, it has to prove it can survive the extreme violence of spaceflight. That proof is extracted at the Tianjin Assembly, Integration, and Test Center. Spanning 100,000 square meters, it serves as the ultimate bottleneck for new spacecraft, forcing every unit through a gauntlet of extreme environmental stress tests. The centerpiece of the facility is the KM-8 Space Environment Simulator. Standing 35 meters high and measuring 17 meters across, it is the largest thermal vacuum chamber of its kind in Asia. Inside the chamber, engineers cycle temperatures from 150 degrees Celsius down to -150. Next, an electric shaker generates 140 tons of force, simulating the violent structural loads of a rocket ascent. Finally, 156 decibels of concentrated sound blast the hardware in a reverberation chamber. Only after surviving this simulated crucible does a mass-produced satellite earn its certification to travel from the inland testing facility to the launch pad. For the heaviest payloads, that journey ends at the Wenchang Space Launch Site on the southern coast of Hainan Island. Wenchang offers a distinct geographic advantage. Because it sits at a low latitude near the equator, rockets launched from here get a significant speed boost from the Earth's natural rotation, allowing them to carry thousands of extra pounds into orbit. Those heavy payloads are carried by the Changzheng, or Long March rocket. This family of launch vehicles is the primary workhorse for the Chinese space program, lifting everything from small observation satellites to massive space station modules. At ignition, millions of pounds of thrust slam into the launch vehicle. The satellite experiences several times the force of gravity, relying entirely on the structural integrity verified in Tianjin to survive the climb through the atmosphere. Once the fairing separates and the payload is successfully inserted into orbit, the physical engineering journey concludes, and the satellite's digital life begins. The exact moment a satellite detaches from its upper stage, command and control instantly hand over to a vast terrestrial network. The central nervous system for this operation is the Beijing Aerospace Flight Control Center, or BAACC. This facility coordinates a global web of ground stations and tracking ships to maintain constant communication with the hardware flying overhead. BeiDou, China's proprietary global navigation system, blankets the planet with precise positioning data, serving as the backbone for international shipping. Alongside BeiDou, the Fengyu series tracks severe weather patterns, while Goffin satellites capture highly detailed 3D topographical maps of the Earth's surface. This massive volume of orbital hardware creates a dense infrastructure that dictates modern agriculture, coordinates global supply chains, and manages disaster response. The ability to field that kind of capability requires a seamless chain of operations. It demands robotic assembly in Shanghai, extreme environmental testing in Tianjin, and equatorial launches in Wenchang. By linking these massive industrial centers, China has secured a permanent, rapidly expanding presence in low Earth orbit. By industrializing the design and testing process, China has built an ecosystem capable of populating and maintaining the next generation of global orbital networks.